So today we're going to go more into average rate of change, but it's going to be a very short lesson of change. And let's call this part 2. It's going to be very short. So the key thing you need to know is with linear equation, average rate of change is the same thing as slope. For linear equations, average rate of change is slope. Now, when we're talking about different types of equations, like maybe a very weird curve, it is not slope. It is instead the slope of the secant line, to be precise. But when I say for a linear equation, it is the slope, that means we can say slope is equal to y2 minus y1 over x2 minus x1. And you can alternatively write this, if we're not using a's and b's and using x and x1 and x2, you can write this as instead x2 minus x1 over the outputs of these values. Now, if you use a's and b's, it does not really matter. Those are just arbitrary values we'll be using. So this is just what people have listed it. I just want you guys to be comfortable in different types of notations for slope. So we can say average rate of change for linear equation is just slope. Well, the whole point of 2.5 is talking about linear models. And before we even go into linear models, we need to know how to identify linear equations. Identify. And for the most part, we should be comfortable in identifying if it's a linear equation. How do I know if it's a linear equation? Well, you need, first of all, you want to have it in the form of mx plus b, but sometimes it's not always going to be in this form. So how do you know if it's a linear equation? Well, the key thing is, what is the exponent? Exponent of my x has to be 1. The degree has to be 1. So example, if I have y equals 4x squared plus 2, not linear. That's a clear one. Now, what if instead I had y is equal to, let's say, 3 times x plus 2? This is linear. You would actually have to distribute this out to determine if it was linear or not. And if you distribute that out, you get 3x plus 6. This is your slope. This is raised to the first power, so it is linear. And of course, this is your y-intercept. And then, you might see some even weirder behaviors, like maybe if you had an example like this. Is this a linear equation? Right here. Is this a linear? Well, the highest degree for the exponent, you have to actually calculate this one out, which some people aren't used to calculating out. Remember, we can turn this into two separate fractions because x divided by 5 plus 2 over 5. If they have the same denominator, I just add the numerator. I'm just going in reverse direction. Well, if you rewrite it as that way, technically speaking, there's a 1 here. That means I have 1/5 times x plus 2 over 5ths. So this right here is to the first power. So this is linear. And in this case, my slope is going to be 1/5. My y-intercept is 2/5. Being able to play with your algebraic expressions without, breaking any logical rules is very important when identifying what's a linear equation or not. So, I want to actually talk about a slight word problem. I want to talk about one word problem in particular, and then I just want to talk about instantaneous rate of change, and then we'll end it off. So let's have a word problem, and let's make this the time axis, and let's make this distance. Let's say 10 feet, 20 feet. I don't want to do feet. That's too slow. Let's do a mile. These are in miles. Yeah. Miles. So this is 1 mile, 2 mile, 3 mile, 4 miles. All right. And then I were to ask you, hey, which one of these graphs, if the graph here represents, if the linear equation here represents the speed a car is going, if this graph represents speed of car A, speed of car B. If this was speed of car B and speed of car A, and I might ask you, what is the average rate of change? Which car is faster after, let's just say 1, 2, 3, 4. These are minutes. After 2 minutes. Which car is faster after 2 minutes? Well, you might need to calculate, or if you can understand this visually, but you might need to calculate the slope of these lines. So I might have to calculate the average rate of change. So let's calculate the average rate of change from 2 to, let's say, 4. 4 minutes. And we do 2 to 4 as well. Well, we're going to have to calculate slope. Rise over run. How much did I rise? 1, 2, 3. And I ran 2 in this case. Over here, I rose 1. And then I ran. See, I rose 1 over here. And then I ran 1, 2, 3. So, car A, and we have to understand this in context. Car A traveled at an average rate of, let's see, we rose 1 mile, so it's 1 mile over how much time? 3 minutes. That's its speed. Car B went at a speed of, my rise is 3 miles over 2 minutes. And if I simplify that, that becomes 1.5 miles over 1 minute. And if I simplify this, we can simplify this into, let's see what I want to simplify that to. 0.333 miles for every minute. And all I am is dividing them out. Boom. So now we got to decide which car is going at a faster rate from after 2 minutes to 4 minutes. Well, we're going to be choosing the higher value of our slopes. And the higher value of our slopes is going to be car B. 1.5 is bigger than 0.33 over 1 mile. These are both over 1 mile. So I have to have the same ratio or the same denominator to make a good comparison. But I get car B travels at a faster rate. And that makes sense. This already visually looks like it's steeper. The one that is steeper is going to tell you what has the faster rate of change. Now, the one that's less steep is going to be slower. Now, when I say the one is less steep and more steep, I don't mean just negative or positive slopes. I mean the larger of the absolute value of a slope. So, what I mean by that is if you had a negative slope, all that entails is that your function will be decreasing instead of increasing. However, your steepness is still 2 steepness. It's just in the other direction. So the negative doesn't really play a part in the steepness. It just tells you which direction your steepness is. And then the last thing, so that covers word problems. And then I encourage you guys to read the book and then try these problems out. We have work with some word problems with linear equations, so you guys should be able to do these questions. And then the last thing I want to talk about is instantaneous rate of change. We talked about this briefly, but I want to go into more. Instantaneous. I can't spell. Instantaneous rate of change. The idea that I initially described was, let's draw this out. You had f. Let's suppose we had a function f. This is f. You have f. Locate at some a plus h minus f of a all over h. Well, the idea of this story is that we have a, and then we're going to increase that a value by some small number h. So let's make h somewhere over here. Let's make it a very small number. Let's say this a plus h. We're going to add that by a very small number. And the reason why we do this, if we think about it as a speedometer case, when we're tracking the speed of a car, you don't necessarily want to track the speed of a car from one point to a point very far. If you want to keep a good accurate speed, you got to continuously track each small little interval. So we're going to take a very small number h, and we're going to add that to our a value, and then we're going to use that to calculate the slope between those 2 points. So if we get this point over here and this point, well, that's the same thing as saying, this is the exact same thing as saying f of a plus h minus f of a, those are my outputs, over my inputs. But then the thing with the inputs is that the a's cancel out, and that is why we get exactly this. So we're trying to see, hey, if we have our speedometer, how fast are they going if the second point that I take is super close to my a value? It is super close. Well, now we have a little exercise I want to try out. So this is just the intuitive concept. See how very close they are together. F of a. The outputs are also very close. That's what I mean by instantaneous. So let's take an example. Let's say I have 2x plus 3. F of x equals 2x plus 3. Let's calculate f of a plus h plus h. Oops. Let's calculate f of a plus h minus f of a all over h. Let's see what happens if we calculate this. They call this the difference quotient as well. Quotient. If I calculate the difference quotient, well, I have to calculate f of a, which is going to be 2a plus 3. Then I have to calculate f of a plus h, which is 2a plus h plus 3, which is going to give me 2a plus 2h plus 6. Or plus 3, I'm sorry. Plus 3. So if I calculate all of this, I get I'm just going to be replacing values now. 2a plus 2h plus 3 minus 2a plus 3. Put a parentheses. Don't make that mistake. All over h, which to deal with minus sign, turn this into plus, make these subtraction symbols. And then we get the 2a's cancel out nicely. So we get this cancels out. The 3's cancel out. We're left with 2h over h. If we simplify it, we're left with 2. Okay, so that's nice. And it just turned into a single constant. Now, let's do another one. Let's do something like, let's let g of x equals x squared plus 1. I don't want to make it too complicated, but let's just do x squared plus 1. And I want to calculate g of a plus h minus g of a. And you'll see the motivation after we calculate all this, what I'm trying to show you guys. Well, let's calculate g of a plus h, or g of a. And that's going to be a squared plus 1, g of a plus h which is going to be a plus h squared plus 1, which is equal to a squared plus 2ah plus h squared plus 1. Remember, you cannot do that. You cannot apply that power like that because there's two terms. Instead, you have to FOIL it out. Well, now if you calculate this, this becomes, oh, it's already simplified. So I have these terms. Now let's actually calculate this rate of change, this instantaneous rate of change. If I were to calculate that out, I get a squared plus 2ah plus h squared, and is plus 1, all subtracting a squared plus 1 over h. And then if we cancel things out, if we turn this to plus sign, I turn these to minus signs, now I can cancel things out nicely. This guy cancels out with this guy cancels out with this guy, so we're left with equal 2ah plus h squared over h. I can pull a GCF of h. I get 2a plus h all over h. I have one term on top, one term on bottom, which means I can cancel out. Boom. Nice. And I'm left with 2a plus h. So, why did I do all this stuff? All right. I want you guys to make the comparison between this first difference quotient over here, this first instantaneous rate of change, the one I did over here. And then I want to, in particular, compare it to what happened down here. Well, you'll notice that in our linear equation, this is a linear equation, in our linear equation, we are left with a constant. There's no a, there's no h, and I'll explain why. Over here, we do have an a, and we do have an h. What the heck does that mean? Why? Well, in our linear equation, let's say I have a line. If I were to find the slope, the instantaneous rate of change, which is just the slope at the very smallest points next to each other. If I were to calculate that, well, it doesn't really matter. The slope between these 2 points, right here, is the exact same thing as the slope between these 2 points. It doesn't matter where you're on the line. Your slope will be the exact same. So it's a constant because does not depend on a, which means location of point. It does not depend on where you're at on the line. It does not. You will have the exact same slope throughout the entire line. Choose any 2 points. You can choose the furthest one away, and you can choose the one next to each other. They will be the exact same slope if you simplify their ratio. So that's the power of finding the average rate of change or instantaneous rate of change of a linear equation. You will always get a slope, always get a constant. You will always get a constant slope. However, over here, what this means is that the a value means it will depend on location. It will depend on where you're at. And wherever you're at, it's going to have a constant added. Now this should look familiar to you guys though. This form, 2 times a variable plus a constant. Well, if you guessed it, this is a linear equation. This is very strange. So earlier when we had a linear equation and we found the instantaneous rate of change, we have a constant. However, when we did a quadratic over here, x squared plus 1, this is a quadratic. When I did my instantaneous rate of change, I get a linear equation. So that's going to bring into some interesting rule. We'll realize that every time we calculate the instantaneous rate of change of a function, it's actually just 1 degree below the original polynomial. If you have a quadratic, it goes down 1 power, linear. If it's linear, it goes to a constant. If it's cubic, it goes to a quadratic. Your rate of change will always be 1 degree lower than whatever your other degree of the original equation was. So that's a very interesting property. So for linear equations, once you calculate that, the instantaneous rate, or for quadratic, once you calculate your instantaneous rate of change, it will depend on your location, and it's going to add a small little constant. Whatever h value you make very small, it'll add that to it. So that is the idea. Now, of course, there's little thing that I don't mention here, but you cannot have h equals 0. And that's kind of obvious because you can't divide by 0. So the constant has to be super small. So that's the idea of working with average or instantaneous rate of change for different types of equations. And that'll end today. I wanted to make this video very short. So I encourage you guys to try some word problems in the book. They have some really good word problems. And make sure you have an understanding of what it means for instantaneous rate of change, average rate of change, slope. Some of them mean the same thing, but there's small little subtlety that plays in. And I will catch you guys later. Take care. Bye.